Right here we have our camshaft position sensor, and in the back here we have our crankshaft. Today we're going to talk about the crankshaft position sensor on an 05 Suzuki Verona. The electronic connection system uses a magnetic crankshaft sensor. The sensor is mounted 1.3 millimeters from the crankshaft reluctor. The reluctor is a special wheel attached to the crankshaft with the slots machined into it. They are equally spaced. The last slot is wider and serves as a generator as its sync pulse. As the crankshaft rotates, the slots in the reluctor changes the magnetic field in the sensor, creating an induced voltage pulse. The longer the pulse, the last slot identifies a specific orientation of the crankshaft and allows the ECM to determine the crankshaft orientation at all times. The ECM uses this information to generate timed ignition pulse that is sent to the ignition coils and the fuel injectors. Here's the wiring diagram of the crank sensor. Here's the ECM. We have high ref, low ref, and ground. Each of the color designated is correctly with the wiring on the vehicle. Up here is the fuse block. It is hot at all times, and there's the main relay. With the green, I'm going to mark where the power is going. So from the fuse block, it goes to the fuse, to the relay once it clicks, all the way to the relay signal to the ECM. From here, it can go to the low ref or the high ref. Once it's producing voltage from the crank sensor, it's gonna go back to the ECM through ground. Also remember, the crank sensor generates its own voltage, as you're gonna see in the next video. We have 1.8 volts for our low ref signal on our crankshaft sensor. Now we're going to talk about the camshaft sensor, which sends a signal to the ECM. This signal is used as a sync pulse to trigger the injector in the proper sequence. It also uses a signal to indicate the position of number 1 piston during the power stroke. This allows the ECM to calculate the sequential fuel injection mode of operation. If the ECM detects an incorrect signal while the engine is running, it will set a code of P0341. If the signal is lost while the engine is running, the fuel injector system will shift to a calculated sequential fuel injection mode based on the last fuel injection pulse, and the engine will continue to run. As long as the fault is presented, the engine can be restarted. As you can see here, we have the wiring diagram of the camshaft sensor. Right here is our camshaft sensor. Down here is our ECM, and up here is our fuse block, which is hot at all times. Here is the main relay. With the green, I'm going to designate the color. I'm going to designate where the power is going. So from the fuse to the relay, all the way to the relay signal to the ECM. Once the relay clicks, power also goes over here, all the way to the sensor, to pin 3. From pin 3, this is our supply voltage. From the ECM here, our signal voltage is only 5 volts. And with the red, it's gonna ground connecting to a wire from the IAT sensor down to the ECM to ground. Here we're getting our supply voltage, ground, and or supply power. This is our signal for our camshaft position sensor. As you can see, the first one is signal, the next one is ground, and the third one should be power.
Okay, and here we have our picoscope reading for our cam position sensor. And now we're going to rev it, and you can see that it increases in frequency and that it is a square wave signal. Okay, and here you have a screenshot of our cam sensor signal at idle on the picoscope. As you can see, we're sitting at around 6.2 hertz at idle, and it is a square wave signal. It goes from 0 to 5 volts, and And actually, if we do the math off of this, 6 hertz is 6 cycles per second. 6 times 60 for 60 seconds in a minute gives us 360 cycles per minute. And say the engine is idling at 720 RPMs, that would give us approximately 2 teeth. Well, there would be 2 teeth on the cam signal. And here you have a screenshot of our pico reading on our cam sensor. As you can see, there are no missing teeth. There's no identifying tooth for the cam sensor. It relies on the crank for cylinder identification. And this is at around 3,000 RPMs. As you can see, it is still a 5-volt signal. It's because amplitude does not increase on square wave signals, only on sine wave signals. And we will see that later with our crank sensor. And here we have a pico reading of our cam and crank sensor overlaid, and this is the high and low reference at once. Okay, here you have a screenshot of our pico reading at idle. As you can see, we have the cam and both of the crank sensor signals. We're sitting around 7 volts of amplitude and 1.3 hertz, and the numbers are actually different for each of those signals, but I believe that's just a refresh rate issue or perhaps some resistance. But as you can see, the next one is much more accurate. And here we have a screenshot of our pico reading around 3,000 RPMs. As you can see, our amplitude has increased dramatically. It is at 15 volts now, and our frequency is at 2.4 kilohertz. And here we have another screenshot of a pico reading. This is with just the high reference from the crank sensor, and then we have an ignition table laid over this for our to give us a full 360 of the engine, and then we have a ruler laid over this as well as our crank signal or cam signal. And here is a close-up of that same pico reading just to give us a better view. And if you count on this, there is 58 sine waves and a 2 sine wave gap, which would give us 60 teeth on the starter, 58 with the gap, 60 divisions on the toner or the reluctor wheel.